Rapamycin may actually act as an immune booster. This is really interesting. Rapamycin increased lifespan, restored self-renewal and hematopoiesis of hematopoietic stem cells, and enabled effective vaccination against a lethal challenge with influenza virus. In this particular experiment, rapamycin more than doubled remaining life expectancy. It looks like a pretty impressive effect. There are some caveats here though. There are definitely sex differences. Rapamycin works for lifespan and a whole bunch of healthspan metrics in both males and females, but there are differences. My name is Matt Caberline, and welcome to the Optispan YouTube channel. Hey everyone, welcome to the Optispan podcast. And on today's episode of the R Files, I want to dive into the effects on rapamycin on the aged immune system. And I think this is a pretty interesting and somewhat complicated topic. Certainly, you will still hear most people refer to rapamycin as an immune suppressant. Obviously, that's overly simplistic, and there is a fair amount of data that, at least in the context of the aged immune system, rapamycin may actually act as an immune booster. And so what I want to do today is take you back to really the first study in mice that I think gave us a hint of this remarkable ability of rapamycin to rejuvenate at least aspects of the aged immune system. So we're going to go all the way back to 2009. This was actually a big year for rapamycin. So this was the year where the classic study from the interventions testing program published in Nature first showed that you could start treatment with rapamycin in middle age in mice and get pretty robust effects on lifespan. And so in that study, they started treatment of rapamycin in mice at 20 months of age, which is about the mouse equivalent of a 60, 65-year-old person. And I've talked about that study in other episodes on the podcast and why, for many reasons, I think that was a pivotal moment in the field. One being that was really the first demonstration with any drug that you could indeed have robust effects on lifespan starting the treatment in middle age. But that same year, there was another study that came out of Pan Zheng's lab at Michigan a few months later that I think is still largely flown under the radar, but really deserves to be right up there with the ITP study in terms of its impact and importance, at least in my opinion. And really, this is one of my favorite papers in the rapamycin literature. So I want to do a little bit of a deeper dive on this paper. So this paper is titled mTOR Regulation and Therapeutic Rejuvenation of Aging Hematopoietic Stem Cells. So there's going to be a lot of language in this paper. So hematopoietic stem cells you can just think of as immune stem cells. And I think there are a few reasons why this paper, hasn't been as widely appreciated as it probably should have. First of all, it was published in sort of an odd place. It was published in what at the time was an e-journal, an electronic journal, which again, this is 2009. Really, that was pretty uncommon. Still, most journals, while they had websites, were still print journals. And this was an only electronic journal, and it was pretty new. It was an offshoot of Science magazine, and AAAS at the time was trying these e-journals. There was actually a Science of Aging Knowledge Environment e-journal. This was the signaling equivalent of that aging e-journal called Science Signaling. And so I think it was sort of missed in part because of where it was published. I think it was also maybe not as widely appreciated in the aging community because it was written like an immunology paper. And you'll see, I'll read the abstract in a minute, and you kind of like, ugh, there are a lot of big immunology words in there. So I think that may have also influenced why this paper sort of flew under the radar for many longevity researchers. Okay, so I'm going to read the abstract and try to, talk through it as I go. So, the abstract starts, age-related declines in hematopoietic stem cell function, so immune stem cells, may contribute to anemia, poor response to vaccination, and tumorigenesis. Again, just saying that declines in stem cell function lead to some consequences as we get older, like the failure of the aged immune system to respond well to vaccines and the failure of the aged immune system to carry out cancer surveillance. Here we show that mammalian target of rapamycin, mTOR, activity is increased in hematopoietic stem cells from old mice compared to those from young mice. And so what they're showing is that if you look at biochemical readouts of mTOR activity in these immune stem cells, that goes up with age. And that's been seen in other tissues as well. So this is maybe not a universal feature of all cells with age, but at least in several tissue types, people have reported an increase in mTOR signaling as part of the aging process. Then they go on, mTOR activation through conditional deletion of TSC1 in the hematopoietic stem cells of young mice mimicked the phenotype of hematopoietic stem cells from aged mice in various ways. Okay, so TSC1 is an upstream inhibitor of mTOR. So when you knock out the TSC1 gene in mice, what you get is hyperactivation of mTOR. And so what they're doing here is, instead of looking in aged mice, they take young mice and they use this genetic manipulation to sort of artificially increase mTOR levels, mTOR activity. And when they do that, what they see is they can recapitulate these dysfunctional phenotypes that go along with aging in the hematopoietic stem cells. So these phenotypes included increased abundance of the messenger RNA encoding the CDK inhibitors P16-ANK4A, P19-ARF, and P21-CYP1, a relative decrease in lymphopoiesis, and impaired capacity to reconstitute the hematopoietic system. Okay, I said that without stumbling. That's good. So let's walk through that. So what they're saying is they take these young mice, they artificially induce mTOR, and they see phenotypes that match what's seen in hematopoietic stem cells from aged mice. Those include these markers, which you may recognize as markers of senescence. So they're seeing evidence for senescence of hematopoietic stem cells and a reduced ability of those stem cells to do their job, to function, to reconstitute the immune system, okay? So again, that's what we would expect if you're getting dysfunctional immune stem cells. Okay, now we're gonna go back to old mice. In old mice, and this is really interesting, rapamycin increased lifespan. I'll come back to that. That's really important. Restored self-renewal and hematopoiesis of hematopoietic stem cells, so it allowed the immune stem cells to start doing their job, and enabled effective vaccination against a lethal challenge with influenza virus. And we'll talk in detail about that experiment. So what they're saying is, in old mice, the immune system doesn't respond well to a vaccine, a flu vaccine, and rapamycin restored that function. And I'll show you that data in a minute. Together, our data implicate mTOR signaling in hematopoietic stem cell aging and show the potential of mTOR inhibitors for restoring hematopoiesis in the elderly, okay? And we'll get to that, like the speculation about what this might mean for immune function in people. Okay, so again, just to summarize, mTOR is hyperactivated in immune stem cells with age in mice. Genetic activation of mTOR in young mice leads to premature immune stem cell dysfunction and expression of senescence markers. In old mice, inhibition of mTOR with rapamycin reverses those phenotypes, rejuvenates immune stem cells, and improves flu vaccine response. And rapamycin increases lifespan in aged mice. And in this case, they did a 6-week treatment, and we'll talk more about the details. Okay, so that's what's claimed in the abstract. I'd encourage you to go dive into the paper if you're adventurous, or you can just take my word for it that they do in fact show, in my view, very good evidence in support of all of the claims laid out in the abstract. What I want to do is take you through 2 of the experiments in detail that I think are, at least for me, the most exciting things that came out of this paper. So the first experiment I want to dive into is this immune challenge experiment, okay? So the challenge here is what's called a lethal dose of influenza. And so the way this is done is it's a dose of flu virus that, when injected into the mice, if they're not vaccinated, leads to death within about a week. Okay, so that's the lethal challenge part. And in this particular experiment, they had 2 age groups. They had young mice that were 2 months old, so very young, and old mice that were about 22 to 24 months old. So again, that's maybe the mouse equivalent of a 65 or 70-year-old biological human. These mice were C57 Black 6 NIA. So again, that doesn't really mean anything to probably most of you, but for those of you who are inbred mouse aficionados, this is, one of the more common inbred strains used in laboratory studies. Really just relevant to note that this is a different genetic background than the interventions testing program. So this paper was in many ways a nice validation just a few months later of much of what was shown in that interventions testing program about lifespan effects of rapamycin in a completely different genetic background, which is really actually very important. And so the treatments here there were two treatments. The control is just what's called a vehicle. So they got everything that's in the vaccine or in the rapamycin, except for the active ingredient, the rapamycin or the vaccine. So that's called a vehicle. You could think of it just like a placebo in a human trial. So the mice were treated for 6 weeks with either the control, the vehicle, or with rapamycin. And this is only in the aged mice. I'll talk about the groups in a minute. And the dose here was 4 milligrams per kilogram given every other day. And again, the dose doesn't really matter other than just recognizing it's very challenging sometimes to look across studies, and figure out what does that mean relative to all the other data on rapamycin. So in the ITP, the rapamycin is given in the food in an encapsulated form. In this study, it was injected directly into the animals at a dose of 4 milligrams per kilogram, and that was done every other day. You'll see in other studies it's injected every day. And so this really makes it complicated. If I had to guess, where would I put this in terms of an absolute dose, it's probably a little bit higher than the 42 part per million dose in the food, which is the highest dose that's been tested by the interventions testing program. In a study I'll come back to in my lab, we actually tested 126 parts per million in the food. We also tested 8 milligrams per kilogram every day. Again, I don't know where this 4 milligrams per kilogram every other day falls relative to those. Certainly it's lower than the 8 milligrams per kilogram every day. Probably somewhere, again, this is total speculation, but probably somewhere between the 42 parts per million and the 126 parts per million. Okay, so that's the dose. So there were 4 groups in this study. The first group is what we call a negative control. No treatment. These mice are young. They don't get the flu vaccine, okay? And so in this case, this is a control because we expect with no vaccination, if they do the experiment right, when given a lethal dose of influenza, it will be lethal and the mice will all die, right? So this is a very important control. It shows that the experiment was done properly. Then there's a positive control, which is the young mice that get the vaccine. So we're taking the aging piece out of the equation. We're giving them a vaccine. And this is why this is a positive control, because if the vaccine worked, the mice should be protected against the lethal dose of influenza because they will mount a protective immune response. Okay. Then there are 2 experimental groups here. The first experimental group are old mice that just get the vaccine. So in this case, we're looking at the effect of aging on the ability of the immune system to respond to the vaccine. The second experimental group are old mice that get the vaccine, but they also get rapamycin for 6 weeks, okay? And here we're looking at the effect of rapamycin on the ability of the aged immune system to respond to a vaccine. And the design here is pretty neat. So again, in the old mouse groups, they get either the vehicle or rapamycin for 6 weeks. Remember, they're 22 to 24 months of age at the start. There's this 6-week period. After the 6 weeks, there's what we call a washout for 2 weeks, and then they get the vaccine. And then we follow survival after that challenge with influenza. And so that's what's plotted here. And I'm going to take you through this chart because I think to me, this was a very powerful figure the first time I saw it. So the first thing to appreciate is what is being shown here. Survival on the y-axis as a function of days after the virus challenge. And remember, this is after that 2-week period and the vaccination. So again, 22 to 24-month-old mice, they get either vehicle or rapamycin for 6 weeks, or you have the young mice that get the vehicle for 6 weeks. Then there's a 2-week period of nothing. And then there's the vaccination. And then right after the vaccination, we give them the challenge with the lethal dose of influenza. And what's being shown here is survival after that challenge. So after all that other stuff that came before. Okay, so the first group we want to look at is the negative control, the young mice that were not immunized. And again, if the experiment worked, and the lethal dose of influenza was in fact lethal, we should see all of these mice die. And that's exactly what we see. Within a week, 8 days, all of the animals have died. The experiment worked. The lethal dose of influenza was lethal in the absence of a vaccine. So what about the positive control? These are also young mice. They get the vaccine, and if the vaccine worked, they should be fully protected against the influenza challenge. And indeed, that's exactly what we see. After 15, 16 days, 100% of the animals are alive. This is, again, exactly what we would expect. Vaccines work, people. If you're a young animal with a functional immune system, you get the right vaccine, you will be protected against the viral challenge that vaccine was targeting. Your immune system will mount an appropriate response. Okay, so the experiment seems to be working. So now the question is, what is the effect of aging on the ability of the immune system to respond to a flu vaccine? And this was pretty interesting to me the first time I saw it. I actually did not expect that there would be such a large degree of dysfunction in the aged immune system. So what you can see here is that at least if you're a mouse, 22 to 24-month-old mouse, if you get a vaccine, there's only about a 30% chance that you will mount a functional response to that vaccine sufficient to protect you against a challenge with that virus. In other words, 2/3 of the mice, 70% of the mice died upon the lethal challenge with influenza, even though they all got the vaccine. Okay, so 100% protection in the young mice, 30% protection in the aged mice. I don't know if it's this bad in people, but we all know there's a decline in the ability of the aged immune system on average to respond to a vaccine. We learned this going through the COVID-19 pandemic, right? So now the question is, what is the effect of 6 weeks of treatment with rapamycin on this defect in the aged immune system? And this was also quite striking. So it turns out there's another curve hidden under the young mice that got the flu vaccine. Those are the old mice that got rapamycin and then the vaccine. There's 100% protection following 6 weeks of treatment with rapamycin. So I think what this clearly indicates is that at least in a mouse, at least using this measure of immune function, rapamycin is able to rejuvenate the ability of the aged immune system to respond to a flu vaccine, at least sufficient to protect the animals against a lethal dose of influenza. Okay, so the take-homes from this experiment are that immune function as defined by response to vaccine declines precipitously with age in mice. And again, this is also true in people. Maybe it's not quite that severe, but there is a decline. 6 weeks of rapamycin treatment fully restored this functional measure of the aged immune system to a youthful state. And I think this is pretty remarkable, given that many people still think of rapamycin as an immune suppressant. And, I get it, because it was used in organ transplant patients to prevent rejection of the organ transplant. But if you only looked at this data, you would call it an immune booster or an immune rejuvenating factor. So context matters, and I think that's important to appreciate. I do think there are a couple of remaining questions that this experiment hasn't answered, and as far as I know, still haven't been answered. I think it's really interesting to ask what would have happened if the mice had gotten the vaccine while they were still taking rapamycin. Remember, there was this 2-week washout period after the 6 weeks of rapamycin treatment before they got the vaccine. Given that rapamycin is, when you're taking it, actively modulating the immune system, it's an important question to ask, would you have gotten the same effects if the mice were still taking rapamycin when they got the vaccine? I don't know the answer to that. My speculation is that you probably would have, but that's speculation, and I think it's an important question. And again, I think we just still really don't know the answer to that question. It's also interesting to think about, what would this look like with other types of immune challenges, say bacterial challenges, or with other types of viral challenges? And I'll come back to that when we start talking about the human data. Okay, so the other experiment from this paper that I want to talk about briefly is the lifespan experiment. So remember from the abstract, they claimed that rapamycin treatment increased lifespan in aged mice. And this is a pretty interesting experiment for a couple of reasons. It was a short-term transient treatment using that same 6-week treatment paradigm. And remember, this was only a few months after the ITP had published their continuous rapamycin treatment starting in middle age. So the design here, it's a similar design with the animals. So they're 22 to 24 months old, same background, C57, Black 6, NIA. They got treated with 6 weeks of rapamycin at 4 mg per kg every other day. Then they stopped the treatment and they followed the mice for the next 30 weeks and asked what was the effect on survival. And again, I think this was sort of unfortunate the way they plotted this figure, because it's plotted kind of the opposite of the way most people in the aging literature think about lifespan experiments. So instead of plotting survival as a function of time, this is plotted as death ratio, or deaths as a function of time. So in this case, more death means the curve is going up instead of the curve going down. And it shouldn't make any difference, but I do wonder if this influenced, part of the reason why this experiment isn't as widely known about or as appreciated. So in any case, the way this is plotted is ratio of animals that have died as a function of time after the rapamycin treatment started, right? So again, these mice are 22 to 24 months of age at the start of this treatment. And if you look out to 30 weeks, what you can immediately appreciate is there's a huge difference, right? The animals that got the vehicle, the control, 80% of them are dead after 30 weeks, whereas the animals that got this 6 weeks of rapamycin, 80% of them are alive after 30 weeks. That's an enormous difference. Unfortunately, they did not finish the experiment. Wouldn't it be really nice to know how big the effect was? We're going to have to live with disappointment, folks, because they didn't finish the experiment. So clearly there's a big effect, but we don't really know how big the effect was. Now, I want to take you through how I look at survival experiments and evaluate them very quickly. And the first thing I always do is I look at the controls and ask, is their lifespan about where we would expect it to be given the literature? And so you almost always are going to focus on median lifespan. And in part, that's because it's really easy to do just by glancing at the figure. So the way you do this is you look at the 50% or 0.5 on the y-axis. And again, it wouldn't matter if this was a typical survival curve or if it's plotted this way as a death ratio. So you start at the 0.5 or 50%. You draw a line straight across to the control curve. And then you draw a line, when you hit the curve, straight down to the x-axis. That is your median survival. That's the length of time at which 50% of the animals have died, okay? So now the question is this normal? Is this what we would expect given the literature? And this is a little squishy, but there's a good rule of thumb that for a reasonable mouse strain, a reasonable mouse experiment in a reasonably long-lived genetic background, you want the controls to be around 850 to optimally 900 days. 800 is okay. Once you get below 800, I really start to question. And when you see controls that live 500, 600 days, I almost say you can't conclude anything from those experiments unless the experimental group lived to like 1,500 days or something like that. So this is also why percent effects can be very misleading, because if your controls are very short-lived, it's easy to get a large percent effect that is meaningless, that isn't real. Okay, so do these look okay? So again, this is complicated. We have to do a little bit of math in our heads here. Remember, the animals were about 24 months of age at the start. So that's going to be, roughly 720 days. And then if we add 15 weeks to that, that's about 105 days. So we're out to 830-ish days, 800 if the animals were 23 months. So it's not great, but it's not bad. It's not so short that I'm worried that this is an artifact, especially given the magnitude of effect from the rapamycin treatment. Okay, that's just a sanity check that's useful to go through. And then, unfortunately, we can't say how big the effect was because we don't know what the median survival was for the rapamycin treatment animal, because at the end of the time they followed the experiment, only 20% of the animals had died. So we can't actually go out and assess what the median was, other than to say the median is more than 30 weeks. So, if we wanted to create a hype filled headline, like has been done recently with a couple of other papers, we would say that rapamycin treatment in this experiment far more than doubled remaining life expectancy of these animals. But we don't know how much more. Maybe it was 2 times, maybe it was 3 times, maybe it was 4 times, we'll never know. So again, I think we have to be careful about the way we interpret these data. But it's also useful to recognize when you see people, jumping up and down, claiming that they have doubled remaining life expectancy in an experiment, you want to look at where the controls were, and you want to recognize that's been done before, more than once. So it's important. That's cool. But it's not as if this is an earth-shattering, never happened before, largest lifespan that anybody has ever seen in the literature. Okay, so in this particular experiment, rapamycin more than doubled remaining life expectancy. It looks like a pretty impressive effect. There are some caveats here, though. So their N is very small. I think there were 10 animals per group. So obviously would want to see this replicated with much larger cohorts. And again, this is a situation where if the effect was small in terms of the magnitude of the rapamycin effect, I'd be pretty skeptical from an N of 10 each group experiment that we can feel much confidence. In this case, given how large the effects were, I think you can be pretty sure this is real. What we don't know is how real the apparent very large size of the effect really is. This was also only in males. It's interesting with rapamycin. There are definitely sex differences. Rapamycin works for lifespan and a whole bunch of healthspan metrics in both males and females, but there are differences. So in the interventions testing program, generally, female mice have larger lifespan extension from rapamycin than male mice do. But there have been a couple of cases, one from a paper we published where male mice actually did better. And I think this is probably both genetic background and dose-dependent sex differences. So we don't know what the effect would have looked like given this design in female mice. And again, as I mentioned, the controls are a little bit shorter lived than what I would call optimal in this genetic background. Fortunately, subsequent studies, including one from my lab that we published in 2016 that Alessandro Bito was the lead author on, have replicated largely the observation that short-term treatments with rapamycin in middle-aged mice are sufficient to very robustly increase lifespan and move multiple healthspan metrics. So in this particular study from my lab, we tested 2 doses. These were 20-month-old mice treated for 12 weeks. So again, 6 weeks in the Zhang lab study, 12 weeks in our study. And in our study, we saw that both doses could increase lifespan. I think the largest effect we saw was about a 60% increase in remaining lifespan. So again, this is nice validation of at least the general observation that transient treatment with rapamycin in middle age in mice is sufficient in multiple labs to robustly increase lifespan. Okay, so as I said, 2009 was a big year for rapamycin. And now let's move to humans and talk about how this work has moved forward into humans. And again, I think, it's fair to say, unfortunately, we still don't have rock solid answers about to what extent are these effects in mice recapitulated in people. But I think we have some evidence to make us pretty confident that, at least to some extent, rapamycin treatment in aged people can have positive impacts on immune function, at least in some individuals. Okay, so the first study I'm aware of that really looked at this was work from Joan Manick when she was still at Novartis, where they published what really is a seminal paper in Science Translational Medicine, where they looked at the effect of 6 weeks of treatment with the rapamycin derivative everolimus on flu vaccine response in healthy older people. So the title of this paper was TORC1 inhibition enhances immune function and reduces infections in the elderly. And this was published in 2014. Again, in this study, they used everolimus. It's what's called a rapalog. It's a chemical derivative of rapamycin. It's also known as RAD001, so the nomenclature gets sort of confusing. I think it's safe to say that the biochemical mechanism of everolimus and rapamycin are identical. They both bind to a protein called FKBP12, and then it's that complex with FKBP12 that goes and inhibits mTOR complex 1. Everolimus has different pharmacokinetics than rapamycin, but again, I think broadly speaking, it's safe to consider them as the same drug in terms of likelihood that they're going to have the same effects in people. The dosing regimen and timing for those effects could be somewhat different between the two drugs. This is the chemical structure of everolimus compared to rapamycin. You can see that they are very, very similar. For those of you who want to get into the weeds on the organic chemistry, the hydroxy group attached to the cyclohexyl moiety has been converted into the corresponding 2-hydroxyethyl ether. Again, you can see by the highlighted areas what that change is. Biochemically, the drugs work identically. Okay, so in this particular 2014 study, they had 218 elderly volunteers, all over the age of 65. They were without unstable medical conditions, so relatively normal health status for their age. They couldn't have, a major unstable age-related disease. This was a 6-week treatment, 2-week washout, based clearly directly off of the Zhang Lab study that we just talked about. Then after that 2-week washout, they got the seasonal flu vaccine, and then they measured antibody response in these people. This was a randomized placebo-controlled trial, so it was the highest standards of clinical trial. There was a placebo, and they had 3 treatment arms. There was a 0.5 milligrams per day everolimus group, a 5 milligram once per week everolimus group, and a 20 milligram once per week everolimus group. And so I think one important finding from this study was really the lack of side effects. So the drug was well tolerated in healthy people, very, very few side effects. Adverse events were comparable actually across groups, with mouth sores being the one adverse event that was clearly associated with everolimus, particularly in the daily use and in the 20 milligrams once a week group. And I think this lack of side effects, with mouth sores really being the only consistent side effect, is pretty consistent with what we've seen from off-label use in people using rapamycin under the prescription of a physician for potential healthspan or lifespan promoting purposes. So I think particularly at the 5 milligram per week dose, there was no statistical difference in adverse events from placebo, even mouth sores. And I think this 5 milligram once a week data here was a contributing factor for why 6 milligrams once a week with rapamycin has sort of become the predominant dosing regimen in people using rapamycin off-label. So in this study, they had a predefined endpoint where they needed to show a 20% improvement for 2 of the 3 flu strains that they were following. And again, remember, there's a little bit of guesswork here because they're guessing in the vaccine what's going to be the seasonally dominant flu strains. And so they had 3 strains they were going to measure. And again, it's important, this was predefined before the start of the study, that they would say they hit their endpoint if they saw a 20% increase in vaccine response. And so for all 3 doses, they saw a 20% increase for at least one strain. For 2 of the doses, the 0.5 mg daily and 5 mg weekly, they met their successful endpoint criteria of a 20% improvement for 2 of the 3 strains. I don't know what it means that there are differences across the strains. Some of this is probably noise. Some of it may be real biology. I don't think we really understand. The thing I thought was, that's interesting for sure. The thing I thought was particularly interesting was how much stronger the effects were in the people who had low antibody responses to the vaccine. So the people who were low responders actually showed a much larger fold change in their response following the treatment with rapamycin. And in this case, all 3 doses against all 3 strains met that 20% threshold for an increase. And this actually fits with other things that I've seen pop up both in my own research and in the literature, not even just with rapamycin, where for any functional measure that you're looking at, there are going to be individuals who are at the low end of the functional threshold for the group that you're looking at, if it's age matched. And it seems to me that often the positive responders the more positive responders are the ones who come in with lower function. That's not shocking. That's actually pretty biologically plausible, but this seems to come up over and over and over again, and I think it's intriguing. And specifically with rapamycin, if you look at our 2017 paper in dogs, where we did a clinical trial for 10 weeks and looked at heart function, there as well, you see the dogs that showed the biggest improvement with heart function with rapamycin treatment were the ones that came in with the lowest level of function at the beginning of the study. So interesting. So since this one, there have been 2 follow-on studies from Joan after she moved to a company called Restore Bio that largely confirmed and extended these results. The 2018 study reproduced everolimus results and also showed that a different mTOR inhibitor called RTB101, it's actually a different class of mTOR inhibitor. It's not a rapalog. It works directly on the catalytic site as what's called an ATP competitive inhibitor. It doesn't bind FKBP12 and work through this allosteric mechanism. Also showed evidence that RTB101 can boost immune function in elderly people. And then there was an interesting 2021 Lancet Healthy Longevity paper from Joan where they did analysis of all of the prior clinical trials, 3 of them by that point with everolimus or with RTB101. It's a pretty interesting read. And one of the statements from that study is the combined results indicate that low doses of the mTOR inhibitor RTB101 are well tolerated and upregulate interferon-induced antiviral responses in older adults. So I'm not going to get into this, but I think this is an interesting, again, theme that we see in the literature where there may be effects of mTOR inhibition on boosting vaccine response in the elderly. There are also maybe different effects on boosting antiviral gene expression more generally. So there might even be some protection against viruses that aren't part of the vaccination. And in fact, there was some data in this paper from Joan that suggested that particularly among individuals who developed severe infections after the clinical trial, so they followed these people over the next flu season, particularly for people who developed severe laboratory confirmed infections, the group that got the mTOR inhibitor were strongly protected against influenza, rhinovirus, and interestingly, coronavirus. So this was 2019 when this study was done. Kind of ironic timing. Wouldn't it have been nice if we had a therapy that would protect people against severe infections from a variety of different coronavirus strains in 2020? We are where we are. But it's intriguing to think about the possibility that short-term rapamycin treatment in healthy older people may confirm long-term protection, at least against severe respiratory tract infections from a variety of different viral pathogens. Okay. And then the last piece of data that I'll just mention comes from this 2023 paper that we published where we collected survey data from people using rapamycin off-label. I've got an entire episode on the podcast where I do a deep dive in that paper. So if you want to look more deeply at that, I'd refer you to that episode. But one of the things we saw in that paper was that among people who used rapamycin continuously and who also had a COVID-19 infection, there was a reduced likelihood, and it was statistically significant, that those people had experienced a moderate or severe COVID-19 infection, severe being defined as needing a trip to the hospital. There was also some evidence that those individuals were less likely to experience symptoms consistent with long COVID. So again, it's intriguing to think about these persistent effects of rapamycin use on immune function, particularly viral infections and severity of viral infections in healthy older people. So I would say, taking this whole body of work, some of the conclusions we can walk away with is clearly in mice, rapamycin strongly rejuvenates the ability of the aged immune system to respond to a flu vaccine. It likely generally improves age-related immune function in mice, or at least immune stem cell function. It can pretty robustly increase lifespan in mice. And then there are at least 4 papers that I talked about, including 3 different clinical trials supporting the idea that rapamycin, as well as other classes of mTOR inhibitors, may have similar effects in people, perhaps generally boosting antiviral effects of the immune system. And speculatively, people who have the lowest level of immune function may be the ones who are going to get the largest benefit in terms of this antiviral boost. So with that, I hope you found this episode interesting, and I hope that if you hadn't seen this study from Pen Zheng's lab, you now have an appreciation for a paper that you didn't previously know about. As always, if you have any comments or questions, I would encourage you to leave them in the comment section below. If you haven't subscribed to the channel yet, please consider doing so. And I hope to see you next time on the Optispan podcast.